which is obviously totally connected to this. All right, yes, question? We will talk about that, but the fertilization obviously has to take place after ovulation. It's usually in a day or so after ovulation is the ideal time. Not the only time, but we will get into that when we get into cleavage reactions with blastocysts. Okay, yes? Yeah, with birth control content, we'll get to that. Yeah, it should be hopeful. I think we're going with your question. Hold off on that because you have to see the actual hormones for it to make sense. Okay? If I don't answer it in my discussion, ask the question. Okay, so let's pull all this together then in the negative feedback. What is going on, I'll put this board back up in a second. Under conditions of low estrogen, you have classic negative feedback. Under conditions of high levels of estrogen, you have positive feedback. What's negative feedback? If I say negative feedback, what should you be hitting me back with? Consistency, right? If I hit you with positive feedback, what should you be hitting me back with? Or what's one word? Or amplification, right? Amplification. And E plus P is inhibition. So what happens is, in the menstrual cycle, the first 7 days approximately, or so, maybe 8 days, 9 days, you have negative feedback. When you have high levels of estrogen, you have positive feedback, leading to the LH surge. Under conditions, we have estrogen plus progesterone, you have an inhibition. No feedback, but a flat-out inhibition, which clamps down on the whole system. And maybe to your question, we had that question about estrogen plus progesterone. You'll see the basis of the female contraceptives is estrogen plus progesterone. You'll see why that is. Okay? So here's what's going on in terms of feedback systems. And the negative feedback part of this has striking similarities to the male negative feedback. You have a hypothalamus, produces GnRH, you should know what this is by now, gonadotropin-releasing hormone, binds to a receptor in the anterior pituitary. And by the way, the receptor here is that 7-pass transmembrane receptor that we talked about. The anterior pituitary produces LH, which binds to the theca cells. And the theca cells convert cholesterol, convert cholesterol to testosterone. And the anterior pituitary also produces follicle-stimulating hormone. Same hormones as males, by the way. Go to the granulosa cells, and this converts testosterone into estrogen. Okay? And this also is then connected. This is also then connected to the follicle, to the primary oocyte. And at low estrogen, there's this classic negative feedback. So when estrogen is too low, you make more of it through the hypothalamus anterior pituitary. The levels start going up. Then you turn it off, right? Turn off GnRH, LH, FSH. You bring down the estrogen. You bring it up again. You bring it down. However, what is going on during this process? What's complicating this? The proliferation of the cells through the LH, FSH, and estrogens. So even though the system is trying to keep the levels constant, there's more cells and more estrogen. So the estrogen levels are slowly moving up with time. And the system can't quite compensate. The negative feedback can't quite work because you have so many more cells. So then you cross a threshold where you have such high levels of estrogen, it is now a positive feedback. And I'll go like this. And at high estrogen, you have a positive feedback. So the more estrogen you make, the more GnRH and LH you make, and then you make more estrogen, you make more LH and FSH. And as a result, you get a surge in FSH due to the high levels of estrogen and this positive feedback. So individuals will cross a threshold from negative feedback to positive feedback, depending on the level of estrogen. When it gets high enough, it becomes a positive feedback. And therefore, you amplify the system. Therefore, you make more LH and FSH, which causes a surge in LH, and you get ovulation. Does everybody see that? Yes?
So when the levels of estrogen are reaching the threshold levels, is the rate constantly decreasing?
Rate of what decreasing? Now, the rate of estrogen is constantly increasing because, in terms of rate is probably similar per cell, but you have a lot more cells. So as you're proliferating the granulosa cells, proliferating the theca cells, you just simply make more estrogen. And the system is saying, well, we want to make this constant, we want to inhibit it. There's so much of it, a threshold is crossed because of the sheer amount of cells, and then you kick in this positive feedback. Okay? Then what happens? After ovulation, you have the corpus luteum, makes estrogen plus progesterone. Even though you have high levels of estrogen, the presence of progesterone changes the regulation by the hormones. And as a result, estrogen plus progesterone completely inhibits the hypothalamus and completely inhibits the anterior pituitary from producing GnRH. You get almost no GnRH and almost no FSH and LH. You completely clamp down the system. The reason is, at least people thought the reason is, after you make the secondary oocyte, you're ready for fertilization, you don't want the ovary to be making any more oocytes. Right? Because you want to keep that one that's potentially going to form a zygote eventually. So that's why it shuts it all down. Yes? It's not inhibition. At low estrogen, it's negative feedback. That is not inhibition. What is negative feedback, everybody? Keeping things constant. So if it gets too low, you make more. If it's too high, you make less. Low estrogen levels here is negative feedback. That is different than inhibition. Up there? That's why they're doing these negative feedback systems. That's the negative part of the feedback system. When it gets too low, that no longer exists. So then you have more GnRH and LH and FSH, and you make more estrogen until it gets too high. Right? Negative feedback is you got to counter the variable. Right? These consistency biological systems is too low, make less. Excuse me. Too low, make more. Too high, make less. It keeps going like that. Okay? So, as was pointed out, how would you make female contraceptives? It's based on synthetic versions of estrogen and progesterone. Because it clamps down on the system. Yes? No. What is negative feedback? You've got to understand the concept of negative feedback. What is negative feedback? You want to keep things constant. So when estrogen is too low, the lines that have negative markings on it no longer exist. So you make more GnRH, more LH, more FSH. So you make more estrogen. And if that gets high enough, you start inhibiting GnRH, LH, and FSH, and then estrogen comes back down. When it's too low, you no longer inhibit, and it comes back up. The idea is, in this window, you have too much of it, you make less. Too little of it, you make more. The idea is consistency. Even though it gives the term negative feedback, it is for consistency. Okay? You have to think about that. If you don't understand that, you don't understand human reproduction. Well, keep working on it. It's very important. That's why we have office hours also. Yes? Say it louder, please. Oh yeah, very good question. What happens to progesterone at the end of the cycle? You lose the corpus luteum, unless you are pregnant, and then it's maintained for the first 3 months of pregnancy, and you'll see how that happens. But yes, then you just lose it, and then you go back to the starting point. Go back, yes. There's a very small role of estrogen in males. Right? There's very little of it, but it's likely involved in bone development. There's a syndrome, I forget the name, where they have defects in estrogen receptors, and they grow on usually large, brittle bones. These are individuals that can be 8 feet tall, but they can almost break their bones from walking a little too heavily when they're big enough. There's an interesting syndrome. I forget the name of it. There's not a big role in males, because we don't have the receptors to respond to it very much. We don't make very much of it, because all of our estrogen gets converted into we never make estrogen from testosterone, because we don't have particularly much aromatase, which is the enzyme that takes the substrate called testosterone and converts it into the product estrogen. We don't have much of that. So we are different. Men and women are different. Yes, there's a question here. Yeah, I'm calling this inhibition because there's nothing to feed back on it. It just clamps this down. There's a difference. Negative feedback means consistency. If it's too high, you go low. If it's too low, you go high. This is just keeping it low. All right? Yes?
Sorry, when you lose the corpus luteum, is that why you have less period?
No, the menstrual flow is due to the endometrium lining. However, when you lose the estrogen plus progesterone, yes, the lining then is triggered to go into the menstrual flow. That is correct. That is correct. Now, given this system, we figured out female contraceptives, well, what do you think is the basis of some fertility drugs? If you showed you all the hormones up here, and I have some of the key ones up there, not all of them, but most of them, if a woman is taking fertility drugs, what do you think that is based on? Pardon? Yell it out. Well, not so much estrogen, but LH-FSH, right, the gonadotropins. And if you give a lot of times a women, there are many situations where a woman is having trouble making enough good enough oocytes, they give them fertility drugs, which is versions of LH and FSH. But then the ovary, remember I said 30 or so develop and one wins out? Women on fertility drugs can have many of these winning out. So that's why you can have multiple primary follicles. So women might not have any pregnancies at all, undergo fertility drugs, and all of a sudden have 6, 7 babies at a time.
What's winning out?
What?
What's winning out?
Winning out is of the 30 or so of these follicles, one is the one that develops. But on fertility drugs, you can have many of them coming out. Okay?
And that one developed by chance, right?
Well, yeah, there's not even clear why, but normally one will win out. Most pregnancies are single babies. And there are twins. What happens to twins? 2 of them come out. I have 2 of my 4 kids are twins. And they're definitely different. They're siblings. One's a boy, one's a girl. I feel like I have 10 kids actually with those 2. Okay? All right, we'll talk about twinning in a little bit. All right, so now, what happens now is, on this is fertilization. And we have time to do fertilization, which is, let me leave this up here. Let me leave that up there. So what happens in fertilization is the following. First of all, fertilization takes place in the fallopian tubes. And we'll talk more about this on Monday, but here's the ovary. This is the fallopian tubes. And the secondary oocyte gets put out into the fallopian tubes, and fertilization takes place here in the fallopian tubes. And after about 6, 7 days or so, the blastocyst will implant the uterine lining. But we'll talk about that on Monday. What I want to talk about is the fertilization process. So the oocyte actually gets kicked out of the ovary into the fallopian tubes under most circumstances. And for fertilization, what happens is the spermatozoa, this is the spermatozoa, the thing with the tail here, has the acrosome at the tip of the head of the spermatozoa, which has enzymes to break down the zona pellucida. The zona pellucida has receptors, or binding sites really, called sperm receptors. And this is to prevent fertilization from the incorrect species. Okay? There are a few species that are close enough that it can work. Have you ever heard of the buffalo cattle story? Okay, cattle obviously taste good. Beef hamburgers taste good for a lot of us. But in the wintertime, cows cannot dig under the snow to get out the grass and everything. So they've lost that instinct. Buffalo, on the other hand, don't taste very good, but they have that instinct of digging in under the snow and getting to the grass underneath the snow. So they came up with the brilliant idea, let's cross a buffalo with a cow. They call it beefaloes. Okay, it's because the sperm receptors are close enough that it can work. And they thought they would get a good tasting animal that can dig under the snow. Guess what? They got a poor tasting animal that can't dig under the snow. But it turned out the beefaloes that eventually worked were 3/8 buffalo and 5/8 cow. And you can get those. I don't know how well that part of the industry took off. But it works because the sperm receptors for cattle and buffalo are pretty close. They allow it. Another example is tigers and lions. You can get, and I think donkeys and horses, or mules and horses, one of the two. Donkeys and horses gives you a mule, right? Yeah. The same kinds of reasoning. That the sperm receptors are close enough to do that. Okay? There's really no species that are close enough in humans to get this to work. So what happens is there's a lot of changes take place. The acrosomes, enzymes, kind of digest the membrane. So what happens is here's the membrane afterwards, and you have the sperm nucleus entering in the secondary oocyte. So here's the secondary oocyte nucleus. When the spermatozoa enters after this fusion, there's a lot of changes. You get after this membrane fusion, you get a calcium wave, and where the spermatozoa hits, there's a wave of calcium that goes around the entire oocyte. The way to visualize that is you throw a pebble in a calm pond. You can see this wave, the rippling effect is what you see. In addition, sodium channels open up. Sodium channels open up, and you get something called the cortical reaction. And what the cortical reaction is very important. Here's the membrane of the zona pellucida, and underneath there are these vesicles, cortical granules. Don't need to know that necessarily. And the cortical reaction is that these granules then move up into the membrane. And then after a while, become part of the membrane. And it changes the membrane structure in a way that prevents polyspermy. After you have that nucleus of the sperm in there, you do not want another nucleus in there. Maybe the basis of an interesting science fiction movie, but not reality for humans. You don't want that extra DNA in there. Put this up, and put this down. So then what happens is, here's the secondary oocyte we're in. You have the nucleus of the sperm, which is haploid. Then what happens is, after all this stuff that goes on, again, is a complete metabolic upheaval. And the secondary oocyte undergoes meiotic division. And you get the ovum nucleus, which is 23 and C. You also get the polar body, which gets kicked out, actually. This actually gets kicked out. then these, so then you have sitting in this cell an oval nucleus and a spermatozoa nucleus. You lose, the nuclear membrane breaks down. I'll bring this board down in a second here. Nuclear membrane breaks down. DNA recombines. You then get a new nuclear membrane formed. And then out of this, what you get is, I'll use this board over here. What you get then is a zygote, which has a nucleus, which is 46 chromosomes, 2C DNA. Everybody see that? So what goes on is the spermatozoa dumps in the nucleus, metabolic upheaval inside the secondary oocyte, which includes the meiotic division. The membranes dissolve, DNA recombines, membranes reform, and you get a zygote, which is a true diploid. And that is taking place right there in the fallopian tubes. Okay? Questions on that? Yes? Yeah, the sodium channels, I didn't even talk about all the changes in ATP and all this kind of stuff that goes on. It's a bunch of stuff metabolically. But that kicks on the meiotic division. But note, it is thought that this meiotic division does not take place until the sperm nucleus is pretty much inside the cell. So you never really have a haploid gamete. You have a haploid nucleus, but not a gamete. Okay? All right, so we will continue with cleavage reactions and blastocyst formation. Have a great weekend, and we'll see you on Monday. Same time, same place.